Today we are going to consider another simple problem in quantum mechanics, infinite potential well. Consider a particle of mass m moving inside a potential well and defined by this potential. The potential is 0 in the range minus a to plus a, and it is infinite at the boundary, that is at x is equal to minus a or at x is equal to plus a. The width of the potential well is given by 2a. The time independent Schrodinger equation for the particle inside the well can be written as d square psi by dx square plus 2m by h cross square. Psi is equal to 0, as we assume that the particle is free to move inside the well as there is no potential acting on it. So let's substitute 2m e by h cross square as some constant k square. Then the equation becomes d square psi by dx square plus k square psi is equal to 0. The general solution to this second order differential equation is a sin kx plus b cos kx, where a and b are some constants which can be determined from the boundary conditions. Here we have two boundaries, one at x is equal to minus a and the second one at x is equal to plus a. As the potential is infinite at these two boundaries, there is no chance for finding the particle outside the well. So the particle is confined totally within the well and there is no way to find the particle outside the well. Hence the wave function must vanish at the boundary of the well. Applying the boundary condition psi of x at x is equal to plus or minus a equal to 0, we have this wave function at the boundaries which is equal to 0. Hence this wave function becomes a sin ka plus b cos ka is equal to 0 at x is equal to plus a, and a sin minus ka plus b cos minus ka is equal to 0 for x is equal to minus a. Since sin minus x is minus of sin x and cos minus x is cos x itself, we can write this equation 3 as minus a sin ka plus b cos ka equal to 0. Adding equation 2 and 4 gives us b cos ka equal to 0. Now if you subtract equation 4 from this equation 2, then you will get another equation, a sin ka equal to 0. From these equations 5 and 6, both a and b cannot be 0 simultaneously, since such a situation will lead the wave function psi of x equals 0, which is unacceptable, or which means that the particle does not exist in the well at all. But in this case we know that the particle is inside the well and hence its wave function must not be 0. The other possibilities are a equal to 0 and b not equal to 0, or a not equal to 0 and b equal to 0. So let's consider each of these possibilities separately. First, let's consider the case a equal to 0 and b not equal to 0. Then from equation 5 we have cos ka equal to 0. Since the values of cosine function become 0 for arguments pi by 2, 3 pi by 2, 5 pi by 2, etc., we can write that this condition cos ka equal to 0 demands that ka must be an integral multiple of pi by 2. So ka equal to n pi by 2 with n is 1, 3, 5, etc. Since k square is given by 2m e by h cross square, we can get the expression for energy of the particle as n square pi square h cross square by 8ma square. This can be obtained by equating these two things, because we have seen we will get an expression for k from this equation as this one, but k is originally given by square root of 2me by h cross square. Comparing these two, we will get an expression for the energy En with n is equal to odd numbers, odd integer numbers 1, 3, 5, etc. The corresponding eigenfunctions are given by psi n of x is equal to b cos n pi x by 2a. Now let's consider the second possibility, a not equal to 0 and b equal to 0. Then from equation 6 we have a condition sin ka equal to 0. We know that the values of sine function become 0 for the arguments 0, pi, 2 pi, 3 pi, etc. However, we do not consider the case n is equal to 0 as this would lead to the trivial solution sin of x is equal to 0, which means the particle is nowhere within the well. So the possible values for Ka can be n pi by 2 with n is equal to 2, 4, 6, etc. Again, the expression for energy can be obtained from the expression for k square 2me by h cross square, and equating these two things we will get the energy as n square pi square h cross square by 8 ma square, exactly similar to what we have seen in the previous case. The only difference is that here we have these integers, even integers 2, 4, 6, etc. And the corresponding eigenfunction is given by psi n of x is equal to a sin n pi x by 2a, where n is equal to 2, 4, 6, etc. And now let's try to normalize the wave functions. Normalization of wave function given by equation 8 leads to the expression integral minus infinity to plus infinity psi n star psi n dx equal to 1. But in this case, this integral we need to integrate only from minus a to plus a, as we are sure that the particle is trapped inside the well. So we don't need to consider the space outside the well. And substituting for this wave function here, we have the square of this wave function psi n star psi n. So we have b square cos square n pi x by 2a dx, and this must be 1 for the normalized wave function. And this cos square term can be simplified using the trigonometric relations. You know that cos square theta is equal to 1 plus cos 2 theta by 2. So if you make that substitutions, this will become 1 plus cos 2 times this argument by 2a. The 2 is taken outside the integral. Now simplifying this, you can see that the constant b is given by 1 by square root of a. A similar normalization on equation 10 leads to a value for the constant a which is same as 1 by square root of a, where this small a is the half width of the potential well. So we have the normalized wave functions psi n of x is equal to 1 by square root of a cos n pi x by 2a for n is equal to 1, 3, 5, etc. and 1 by square root of a and sin n pi x by 2a for n is equal to 2, 4, 6, etc. Thus the complete set of eigenfunctions are given by these two values. So this is the complete eigenfunctions which represents the eigenfunction of the particle inside the box for different values of these integers. For odd integers, it has a cosine nature or the cosine function, and for even integers, it has a sine function form. So plotting these functions, we get like these. You can see that the wave functions corresponding to the odd quantum numbers are symmetric, that is psi n of minus x is same as psi n of x, and the wave functions corresponding to even quantum numbers are antisymmetric. That means psi n of minus x is equal to minus of psi n of x. Now let's evaluate the de Broglie wavelength. So we know that k is equal to square root of 2m e by h cross square, and hence we can write E is equal to h cross square k square by 2m. Since there is no potential acting on the particle inside the well, this energy must be the kinetic energy of the particle. The kinetic energy is also given by p square by 2m, where p is the linear momentum of the particle. Comparing these two expressions, we can see that h cross k is nothing but the linear momentum of the particle. Now de Broglie wavelength is given by the expression lambda equal to h by p, which in this case can be written as lambda equal to h by h cross k. For this problem, we have seen that the only possible values that k can have is n pi by 2a. So putting this in the equation for lambda, we get lambda equal to 4a by n. If we represent the length 2a of this well by the letter capital L, then we can write lambda equal to 2L by n. It shows that only half integer and integer wavelength fits in the well. Combining equations 7 and 9, we can write the expression for energy as En equal to n square pi square h cross square by 8 ma square with n 1, 2, 3, 4, etc. Obviously, the energy is quantized. It cannot have any arbitrary energy value. Since 2a equal to L, the length of the well, this can be written as, this equation can be written as n square h square by 8 ml square, which is same as we have seen for the particle inside a box of length L. Now the energy and the wave function for the ground state is given by pi square h cross square by 8 ma square and 1 by square root of x by 2a, because we have put n is equal to 1, which is the lowest possible value for this quantum number. Thus, any particle confined in a potential well has a certain minimum energy called the 0 point energy, and this is a manifestation of the uncertainty principle. Uncertainty in the position of the particle is of the order of a itself. Then the minimum uncertainty in the linear momentum is of the order of h by 2a. Therefore, the minimum kinetic energy of the particle must be of the order of h cross square by 8 ma square. So that's what we have seen here. So this is a consequence of uncertainty principle.